Anybody have any questions from last time? There's one thing on the homework. I can't remember who brought it into my office, maybe Joaquin, but there's one problem that is a little tricky, and I'd like to give you, point you in the right direction for. There's one where, I don't remember what number it is, but what's the one where you're on a path? The particle is traveling along a path that's like xx squared or something. Oh, no, it's x negative 5x, right? Yeah, the speed is 2x. And so okay, so the path of a particle is x negative 5x, moving in the positive x direction. And the speed of the particle is 2x. What's the acceleration? Okay, so let's draw what's going on. So if that's x, that's y. The path that it's following is like this. And it's moving in the positive x direction, so it's going this way, not the other way. And in order to go from, in order to come up with the acceleration vector, if you have like we know, we've done a bunch of problems where you use the chain rule to go from the velocity vector to the acceleration if you have the velocity vector expressed as a function of position, right? We've done that a few times. This one's different, though, because we have to come up with the velocity vector from the information that's given, and you can probably look at that and recognize that there is enough information there to come up with a velocity vector, but it might not occur to you immediately how to come up with a velocity vector from that. Any questions about, I'm hoping that you'll look at this and see, well, there's a speed, there's something that gives a direction. I could probably come up with a velocity vector. Like, that's what I want it to trigger in your head. Okay, so we're going towards the chain rule. But so how do you get to the velocity vector? Well, the velocity vector, did anyone get through this one? Yeah? Maybe? The velocity vector is the speed times the unit vector, times the unit vector in the direction of the motion. And so we have the speed as a function of time. We have to use this path to come up with a unit vector in the direction of the motion. All right, well, if you have any parameterization of a motion, I don't know when I think maybe you probably talk about parameterizations a little bit at the end of Calc 2 and then more in Calc 3, I think. Okay, so here's the trick to finding that unit vector. If you have a motion that's given by let's say f of q, g of q, then, and so q is just some arbitrary variable. That's your parameter that this motion is defined in terms of. Then taking the derivative with respect to q of this vector gives a vector that's tangent to the path. Exclamation. So that's the key. And this isn't a unit vector. It's not a unit vector yet, but at least then we're on our way. Okay, so we're going to so I'm going to define this non-unit vector, but a vector in the right direction is going to be d dx of x negative 5x. And that gives you 1, negative 5. And looking at the picture, you can see that, it's moving along this line. That vector 1, negative 5 is tangent to that path. You do have to be careful about, so I said we're moving in the positive x direction. If we were moving in the negative x direction, we'd have to take the negative of that vector. Okay, so now we need to, to make this a unit vector, we take the length, 1 squared plus 5 squared, so square root of 26. And so the unit vector in the direction of this motion is 1 over root 26, negative 5 over root 26.
This only works for linear equations.
No, it doesn't actually. It works for any. So if you had a more complicated function, you would just have your unit vector as a function of x, but that would still work fine.
Oh, yeah, I see what you're saying.
Okay.
Yeah.
So then it would just, what that would mean is that at whatever x value, you'd have a function that gave you the tangent to that path, and you could use it exactly the same way.
Definitely.
Just the math would get more complicated.
Why did you take the derivative of the vector that equals?
Because I used this idea that if you have this parameterization of a motion, if you take the derivative with respect to that parameter, whatever it is, it gives you a tangent to the path. And so our parameter was x, and so I took a derivative with respect to the parameter, and that gave us a tangent to the path. In this case, since it's a linear function, you could do it sort of by inspection, like just say, okay, well, I know that the slope is,
You just did how you normally calculate unit vector is all the same though. So why did you take derivative?
I guess I did it because this isn't a method that would work if that function was more complicated. Doing it by inspection you wouldn't be able to do it if the function was 5x cosine x or whatever. You'd have, you know what I mean?
So if you had a more complex function, let's say you had 5x squared and the derivative, and for the x component, the derivative of that is going to be 10x. So then would you take 1 over 10x, like square root of?
Yes. So
So
you'd have, yeah, right. So you'd have 1 squared plus 10x squared, 10x, what did you say? 10x all squared.
Right.
That would be your length, would be a function of x. So it's getting very ugly. And then divide by that function of x. But you would have an expression in terms of x for your unit vector.
Okay. Sounds good.
And then, okay, so now we have this unit vector. So now finally the velocity vector is equal to our speed times our unit vector, our direction vector. So 2x over root 26, negative 10x over root 26. That's the velocity vector as a function of x. And now we're at the place where our other chain rule problems have started. We have the velocity as a function of x, and now the acceleration is going to be dv dx, dx dt, or dv dx times the x component of the velocity. Any questions about that?
So if we had the vector was a function y, so let's say it was like y negative 5y, would acceleration end up be dv dy, dy dt, so then it'd be dv dy times vy.
Yeah, let's just do another one. I couldn't think that fast. So let's say so the path is so let's say it's y squared y. Okay. And let's say the particle's moving in the direction of negative y, just so you see how that one works. Okay, so what would this function look like? It would look something like that, I guess. And the particle would be moving this direction. So to get a vector that's tangent to that path for any y value, you'd go d dy of the path, and since it's moving in the negative y direction, you take the negative of that. So that's where that negative comes from. And so you get 2y1. Then the length of that vector is 2y squared plus 1 squared. So 4y squared plus 1 square root. Yes, it would be, I didn't put in that negative. So negative 2y, negative 1. Thank you. And so then a tangent to that curve everywhere would be negative 2y over that square root, and then negative 1 over that square root. Okay, so that's a frickin' mess. And then imagine your dismay when you realize that, so, oh, I didn't give a speed, but let's say speed of 10 meters per second. So constant speed moving along this path. But now, so the velocity vector is equal to 10 times that unit vector, which is negative 20y over that square root. and negative 10 over that square root. And the exceptionally bad news comes now when you realize that you have to take that derivative. dy dt, which is dv dy times the y component of the velocity. But nobody wants to take this. Nobody. Maybe Mathematica doesn't mind. What?
An insane person, maybe?
Yeah, right. That's true. Yeah, maybe some kind of insane person. But anyways, that gives you the right answer. Pretty cool. You know, one place this could come up, by the way, is when you have when you're doing energy problems. You know, energy problems sort of naturally give you a relationship between a position and a velocity, or a position and a speed, you know, when you're using conservation of energy. And so if you're trying to use an energy approach to come up with an acceleration function, you could use the energy equations to get the velocity vector and then use the chain rule. But I'm not telling you how to do your job. Okay. So the last thing that I want to talk about having to do with, what are we talking about? Particle kinematics. Is rolling without slipping. We'll come back to this when we start talking about forces and rigid bodies and stuff. And it's a natural combination of circular motion and relative motion. Okay, so say that you have an object rolling. If it's not slipping, so you can think of sort of three definitions of rolling without slipping. Three defining properties. The first one is that the velocity of the point in contact with the ground is 0. If it wasn't equal to 0, then the velocity of the point on the wheel would be different than the velocity on the ground, and you can think of that as like a definition of slipping, you know. So at that point that they're in contact, they have to have the same velocity. Second, the part of the acceleration parallel to the surface equals 0 for the contact point. And third, the motion of the center is parallel to the surface. Okay, so let me do an example. Okay, so let's say that there's a wheel with a radius of 0.1 meters. And it's rolling this direction without slipping. And so let's say that we know that the angular velocity is equal to 2 radians per second. If it's moving to the right, what direction does the angular velocity have to be? Yeah, right. So it has to be going clockwise, and then, yeah, so in the negative z direction, if we're using this coordinate system. And that's what I was planning to do. So for now, I'm just going to write this as clockwise. And let's say that the angular acceleration is 10 radians per second squared. And let's say it's speeding up. So if it's speeding up, the angular velocity and angular acceleration have to be in the same direction. And let's say we want to know what are the velocity and acceleration vectors at the center.
What's the radius?
Oh, yeah. And then I guess let's also, after that, let's calculate the velocity and acceleration vectors at the top. Okay, so for part A, that's the center. Call this B the bottom point. And I'm going to start with the, so let's see. We know that, okay, pretend I didn't say those last two nonsenses. Okay, now this is definitive. We're going to do this as the superposition of a circular motion, like a rotation around the center, superimposed on top of the motion of the center. Okay, it's relative motion. So we're going to do this as the velocity of the bottom point relative to the ground is equal to the velocity of the bottom point relative to the center plus the velocity of the center relative to the ground. So this is the velocity B would have if the center was fixed. Okay? So let's think about what we know. Do we know anything about the velocity of B relative to the ground? That's right. That's the one we know is 0. So VB relative to the ground is 0. We're trying to calculate the velocity of C relative to the ground. Do we know anything about this other one, the velocity of B relative to C?
Omega times
Yep,
radius.
that's exactly right. So that's the circular motion. So we know that the velocity of B relative to C is equal to omega cross R. That's circular motion. omega is 0, 0, negative 2. R is this. So if the radius is 0.1, that's in the negative y direction, so that's 0, negative 0.1, 0. Take that cross product and you get negative 0.200. That's in meters per second. Okay, so now we can put it together in the relative motion equation. So we have 0 is equal to negative 0.200 plus the velocity of c relative to the ground. So the velocity of c relative to the ground is, rearrange it, and you get positive 0.2 meters per second, 0. You can leave that third 0 off or put it in. Okay? So relative motion. And now we're going to do the same thing with the acceleration, but we have to use these two requirements for rolling without slipping. So relative motion says that acceleration of b relative to the ground is equal to the acceleration of b relative to the center plus the acceleration of the center relative to the ground. And what do we know about these? We know that this one has no component perpendicular to the surface. That's one of the requirements. And we know that the acceleration of b relative to the ground has no component parallel to the surface. Those are the second and third defining properties of rolling without slipping. This one, so the acceleration of b relative to the ground, that says that an observer on the ground doesn't see any acceleration of that point in contact with the ground. There's no acceleration of that point parallel to the surface. If there was, there still can be centripetal acceleration, but it can't have any acceleration that slides it parallel to the ground. Otherwise, that would be slipping. And then this one says the acceleration of the center of the wheel to an outside observer doesn't go up and down at all. It goes smoothly parallel to the ground. Okay, so those are the requirements. All right, so what do we know? So the acceleration of b relative to the center. This is the one that, this is a circular motion, assuming that that center was fixed. So what's the acceleration of b relative to the center. That's right, watermelon equation. Just like we used that velocity equation for this term in the velocity relative motion. So alpha cross r plus omega cross r. This is the term. Okay, so let's see. This term is parallel to the surface. Because that's the tangential acceleration. So we know that alpha cross r is equal to zeros. And then the acceleration of, B relative to C. B relative to C. Now, we don't know anything about that one. Just use your little electronic erasers and there won't be any residue. Okay, so now the two that we do know something about. Acceleration of B relative to the ground. That is equal to so we can break that up into a part that's parallel to the surface plus a part that's perpendicular to the surface. And we know that this one is equal to 0. And then the acceleration of C relative to the ground. Okay, so acceleration of C relative to the ground is equal to a parallel part plus a perpendicular part, and we know that this is equal to 0. Okay, and now we're solving for, let's see, we're solving for the acceleration of C relative to the ground. Okay, so acceleration of C relative to the ground. Sorry, this is so confused. Acceleration of C relative to the ground is equal to B relative to the ground minus B relative to C. Which is equal to B relative to the ground. Okay, so we have a perpendicular part. What am I doing here? Can someone tell me what I'm doing?
Why don't you do ABC? Because you have all
Uh-huh.
So you do ABC, and then you know AB ground, you're going to have the perpendicular component, so then you solve.
ABC. Okay, so I have ABC. That's this one. And I know that... Okay, forget all this. Don't do it like this. This is too much logic for me. Scratch that all out. Do it like this instead. Okay, so we know that the velocity of C relative to the ground was equal to negative omega r 0, 0. So that's what we came up with if we would have kept this all symbolic from the top. And so the acceleration of C relative to the ground is just the time derivative of this. And so that's equal to negative d omega dt times r plus omega times dr dt. That still has a negative. Dr dt doesn't change. And so you just, and d omega dt is alpha. So you just get negative alpha r. Okay, so negative alpha r, that is negative 10 times 0.100 equals negative 1 radian per second squared 0, 0. Okay, so do it like this. Use relative motion equations for an expression for the velocity of the center relative to the ground. And then take the velocity of the center relative to the ground to get the acceleration of the center relative to the ground. Yep.
Shouldn't that be meters per second squared, not radians?
Yes, it should. You're right. Yep. That much I know. Okay, I guess we better do another example of that. Let's finish this one, though, first. So now we want to calculate the velocity of the velocity and the acceleration of the top point of the wheel. So the velocity of the top relative to the ground is equal to the velocity of the top relative to the center plus the velocity of the center relative to the ground. the velocity of the top relative to the center is omega cross r. So that's 0, 0, -2 crossed with the r vector to the top. So now here's the center, here's the top. This is the r vector. And so that's 0, 0.1, 0. And so you get positive 0.200. The velocity of the center relative to the ground, we calculated that in A, and that's equal to 0.200 from part A. And so the velocity of the top relative to the ground is 0.200 plus 0.200 equals 0.4 meters per second, 0, 0. So the top of the wheel is moving twice as fast as the center of the wheel. And then for the acceleration, so the acceleration of the top relative to the ground is equal to the acceleration of the top relative to the center plus the acceleration of the center relative to the ground. The acceleration of the top relative to the center, that's circular motion, so that's alpha cross r plus omega cross r. So that is 0, 0, -10 crossed with 0.10 plus omega 0, 0, -2 crossed with the quantity 0, 0, -2 cross 0.10. And that is 100 plus 0, 0, -2 crossed with 0.200. And that is 0, -0.40. So 1, -0.40. The acceleration of the center relative to the ground. We did that one in part A. -100. That shouldn't have been a negative. That should be a positive. Let's see. Oh yeah, because this is a negative 10. So this is a positive. Okay, so 1, 0, 0. So the acceleration of the top relative to the ground is 1, negative 0.40 plus 1, 0, 0 equals 2, negative 0.40. So why did we have only an x component of the acceleration for the center, but now we have a y component for the acceleration of the top? What's the difference there? What does the... It's the centripetal, yeah, exactly. That's the centripetal acceleration of that point on the top rotating around the center. The center doesn't have any centripetal acceleration. Okay, let me do one more very quick one. This is a major issue for me right now, this time of year. Why do my feet get so cold when I bike? But my hands don't. The answer to that is, so if this is my bike moving along at let's say 10 meters per second. No, let's stop and I'll do that next time. All right, you win some, you lose some. Next class is going to be better. Okay, so Friday is the quiz. So the quiz is going to cover all the things on the homework assignments since the last quiz up through today. Okay.